Hello everybody. In this part, we are going to talk about inverse transformation, which is from section 1.8 and 1.9. In this part, we are going to define inverse transformation and one-to-one onto mapping. And for a given linear transformation, we are going to know how to identify a given transformation is one-to-one and onto. Alright, first we start the definition. What is onto mapping? So a mapping T from n-dimensional space to m-dimensional space is said to be onto if each B in the range is the image of at least one X in the domain. So from the picture, we can see that there's a T, linear transformation. You have 2D plane, Rm plane, and there is a range, Rm plane. And T here, mapping this domain into one plane in the range. And this doesn't occupy the whole domain. Then this is not onto. But on the other hand, the left picture, there's a T, linear transformation, and the domain maps to range, and the range is just occupied. It's just covered by transformation of the domain. Then T is onto. Now let's discuss what is one-to-one mapping. So again, we're going to give a definition and a intuitive diagram, and later we will see how does it apply in examples and get better understanding. So mapping T is said to be one-to-one if for each B in the range is the image of at most one X in Rn. So from right hand side, first counter example. So suppose this is domain and this is range. If you have some point which is coming from multiple sources in the domain, then this is not one-to-one. And if this in the range, if every point has at most one source coming from domain, then this is one-to-one. And one-to-one sometimes is called one-to-one is sometimes called injection, and onto is called surjection. This is different terminology, and it may be mentioned in our homework. Now here is how we apply this in the linear algebra. So T is a linear transformation from n dimension to m dimensional space with standard matrix A. Then T is one-to-one if and only if Ax equals 0 has only a trivial solution. So this means uniqueness. Now, this is uniqueness of A0. Now let's jump to the last term. T is one-to-one, or A is one-to-one, if and only if all columns of REF of A are pivots. So for example, if you want to identify uniqueness of this augmented matrix A and 0, then what you should do is reduce this augmented matrix to REF form and see if there is free variable or not. If there is free variable, then uniqueness does not hold. In other words, to get uniqueness hold, what you want to do is identify all columns are pivots. There's no free variable. Now T is onto if and only if ax equals y has a solution for any y in Rn. So in that case, we want to make sure ay is consistent for having solutions for any y. Now, this is equivalent to say A is onto or T is onto if and only if the last row of REF of A is a pivot. So for example, if you have an REF with something like this, and suppose the first one is 1 and the last row is just 0, then this is not going to be not consistent when you get another y which is like 0, 1. Then this is not consistent. So from this example, we can identify that we can understand why this rule works. So T is onto if and only if the last row of A is pivot. So important thing is two rules. From REF, you can identify A is onto or A is 1 to 1. And we say A is 1 to 1 and onto, then we say A is bijection. So this is the same meaning. So these two are equivalent. Now we are going to look at one example. Let T be the LT linear transformation whose standard matrix is given by 3 by 4 matrix. Then we know that T, first of all, its domain is R4 and its range is R3. Now is T onto? So to have T is onto, we have to look at this. T is onto if and only if last row of REF of A is pivot. So we're going to first calculate for REF. So to get REF, first of all, this is already given as staircase, which is REF. Now from REF, so T is onto if and only if REF has no 0 rows. Then the last row is not 0. Actually, each row is non-zero. So it is onto. Now T is 1 to 1 if and only if REF has no free variables. This is the same thing. So what we can say is first x1 has pivot here, x2 has no pivot, has pivot 2, x3 has no pivot, so this is free variable, and this one is basic variable. So because x3 is free variable, t is not 1-to-1. Now let's talk about new concept, which is inverse transformation. And here we introduce inverse transformation, and we are not going to involve in computation of inverse transformation. So actually this concept leads to what is inverse of the matrix. And that goes to next slide. So what is inverse transformation? Suppose there's a linear transformation T, which is from n dimension to n dimension. So we require the same space for domain and range. In this case, we can talk about inverse transformation. So if T inverse satisfies T inverse composite T of x is the same as x for all x, then T inverse is called inverse transformation. For example, like if you have like this kind of image originally, and if you have T here, and that gives you somehow different image, and then if there's another image, we can name it as T inverse. If this transformation get it back to the original image, then T inverse is this is called inverse of T. And T has its inverse if and only if T is 1-to-1 and onto. So that's why we are going. We had mentioned what is 1-to-1 and onto. This is a necessary and sufficient condition for the existence of inverse transformation. So let's look at one simple example to motivate the next concept of inverse of the matrix. Suppose T is R2 to R2 linear transformation, which is defined as scales each entry by 2. What it means is this. T is from x1, x2, scales to each entry by factor 2. Then find the T inverse. And find the standard matrix of T. And describe T inverse. And find its standard matrix. And what is the product of the two standard matrices? So first, we're going to copy the definition of T. And standard matrix of T is TE1, put TE1 and TE2. So TE1 is 2 times 1, 2 times 0, which is 2, 0. TE2 is 2 times 0, 2 times 1, which is 0, 2. Now, what is A, standard matrix? A is 2, 0, 0, 2. Now, second, what is T inverse? So if we look at this linear transformation, every entry will be stretched by twice. In other words, if you want to have T inverse get back to the original image, then you should take each entry of the new image into half to get back this. So this is T inverse. So if you have x1 and x2, then you should scale this back to 1 half x1, 1 half x2. And then from here, its standard matrix is T inverse E1, which is 1 half 1, 1 half 0, which is 1 half 0. And T inverse E2 is 1 half times 0 and 1 half times 1, which is 0, 1 half. So the standard matrix of T inverse is A inverse, which can be written as this. Now, number 3, we're going to multiply two standard matrices and see if you can get something. So the first one is 2, 0, 0, 2, and this is 1 half 0, 0, 1 half. And if you multiply together by matrix multiplication, this is 1, 0, 0, 1, which is identity matrix. Now, this leads to our next definition in the next lecture. What is inverse of a matrix? So we will see that, we will define that if another matrix multiplied to A, the result, the product of two matrices is I, then these two matrices are inverse to each other. And how to compute this inverse? This is a big topic, and which will go to next slide. Thanks for watching.